In the previous lecture, we discussed about how flip-flops can be used to count the number of clock edges, either rising edges or falling edges, that is the positive edges or negative edges. So we saw how we can design using T flip-flops a circuit that is called as a counter. We can count 2 bits, 3 bits. So if it is a 2-bit counter, we can count from 0 to 3, that is a total of 4 states. And if it is a 3-bit counter, we can count a total of 8 states, that is from 0 to 7. Now, if you quickly take an example, we saw that you have these flip-flops and so on. So we had used T flip-flops. So we'll call this as 0, T0, Q0, Q0 bar, T1, Q1 and Q1 bar, where we are essentially tying the T input of both the flip-flops to 1, thereby making use of the toggling phenomena that is available in the T flip-flop. So if we put T as 1, then the next state will always be the complement of the present state, and that is basically the thing that we are using for counting. So the main clock comes over here. We had assumed negative edge triggered flip-flops, and we see that the clock for the second flip-flop is nothing but the state output from the first flip-flop. So therefore, such circuits are called as asynchronous circuits. Or asynchronous counters. Why? Because the clock for different flip-flops is different. So FF is the short form for flip-flop. So a circuit where the clock signal for different flip-flops is different, that is called as an asynchronous circuit. In this case, it's an asynchronous counter. It is also called as a ripple counter. The word essentially comes from the concept of the ripple carry adder, where the carry from one stage is fed as the carry input to the next stage. So essentially something very similar is happening over here in principle. So therefore it is also called as a ripple counter. So this phenomena can also be modeled using a JK flip-flop, because if you recall, this Q bar being the next state is also available for the JK flip-flop. So therefore, if you want to use a JK flip-flop, all you need to do is essentially tie both J and K inputs to 1. Because when J and K are 1, the next state will be the complement of the present state. So in that way, these both will work exactly the same. Now, we had taken an example to see how flip-flops can count from 0 to some number, and we had essentially seen the example using a special case where the clock is negative edge triggered, or the flip-flops are negative edge triggered, that is, they respond to the falling edge of the clock. Now, what if the flip-flop is a positive edge triggered clock? Will it still count the exact same way as the case for a negative edge triggered flip-flop? Let us try and see. So let us take the simple case of a 2-bit counter, and let us say these two flip-flops are now positive edge triggered. So let us say this is T0, Q0, Q0 bar, T1, Q1, Q1 bar. So once again, we will put T0 and T1 both as 1. There is no need to change that because we will still try to use this particular phenomena of the T flip-flop. Now, suppose we connect the clock of the second flip-flop as Q0, which is very similar to what we have been doing so far. Now let us see what will happen. If the clock signal is something like this, now we have to look at the positive edges. So again, if you assume that Q0 is initially 0, this will become 1 at the first rising edge. In the next rising edge, it will become 0. Then again, it will become 1. Then again, it will become 0. Now, Q0 is being used as a clock for the next flip-flop. So we have to again look at its rising edges. So therefore, Q1, if you assume it is initially 0, will again transition during the rising edges of Q0 only. So here it will become 1 and it will stay as 1 until this point. So what are we noticing? The state values. If again I assume that Q1 is an MSB, if I am considering this as a 2-bit output, Q0 and Q1, for this period the value is 1 1. Then the value is 1 0. Then we get 0 1 and finally we get 0 0. So effectively, if you look, this is 3. This 2-bit value is 2. This is 1 and this is 0. When you compare it with the previous case, what we had seen was it was 0 0, then 0 1, then 1 0, then 1 1. This was the sequence. But here it is the opposite. Here it is counting the reverse sequence. Here in case of the negative edge triggered flip-flop, if we have this kind of a connection and we get that the outputs are essentially incrementing by 1, we call this as an up counter. That is, it increments by 1. This is called as a down counter because it decrements by 1, and both are very, very useful. They have their own uses. But the question is then, can positive edge triggered flip-flops be only used for down counting, not for up counting? Well, no. In that case, what you can do, rather than looking at Q1 and Q0, we can look at Q1 bar and Q0 bar. That we can look at, because they will be exactly the opposite of Q0 and Q1 respectively. Let's see how that works out. So same circuit using the positive edge triggered flip-flops. So let's quickly draw the waveforms without drawing the circuit diagram all over again. So Q0 looks like this. Q1 looks like this. So now let us draw what is Q0 bar and Q1 bar. So Q0 bar will be just the opposite of Q0. So initially it will be 1, then it will go to 0. Then over here it will go to 1, again 0, again 1, like this. Now Q1 bar will be the opposite of Q1. So until here it will be 1, then 0 all the way till here, and again 1. So again, if you assume that Q1 bar is the MSB of the 2-bit number, that is these two, you see this is 0 0, 0 1, 1 0 and 1 1. So therefore you can easily achieve this up counting by making use of the positive edge triggered flip-flop as well. So there is not much difference with the negative edge triggered flip-flop in that matter. Now, in the previous lecture, we had asked a question. Suppose I have a 3-bit counter. Normally it can count from 0, 1, 2 all the way till 7. Now suppose I ask, I want to use the same circuit to count up to 5. That is like saying it will go from 0, 1, 2, 3, 4, 5 and then again back to 0. Normally what happens? After 7 it becomes 0 again. Just like in this circuit, if the next clock pulse comes, these both will become 0 again. So after reaching the maximum count, usually the next count goes to 0 because beyond the maximum count is not possible. Now suppose I want to make this. I want to make this circuit that counts up to 5 only. So the next question is, how many flip-flops will I need? So obviously, number of flip-flops, as we had established a relation, it's the ceiling function of the log of the count to the base 2, and that you get as 3. Because 0 is 0, 0, 0 and 5 is 1, 0, 1. So therefore, you still need 3 flip-flops. That is 3 bits of counting, 1 flip-flop for every bit. So therefore, let us draw the circuit. Let us continue using negative edge trigger flip-flops and see how it works. So therefore, what we are now essentially trying to do is we are trying to achieve a mod 6 counter, because a mod 6 counter counts from 0 to 5. In the previous lecture, we had established that a mod n counter counts from 0 to n minus 1. So let's say this is T0, Q0, Q0 bar, T1, Q1, Q1 bar, T2, Q2 and Q2 bar. So this is the clock that is coming to the negative edge trigger flip-flop. Then Q0 is being fed as clock for the next flip-flop. Likewise, Q1 is being fed as clock for this stage. So this circuit we already know. This counts from 0 to 7. This particular circuit counts from 0 to 7. So after 0 we get 1, then we get 2, then we get 3, then we get 4, then we get 5. Now once 5 clocks have come, when the 6th clock comes, this circuit will try to show 6. This is what is expected. But we want that right after 5, the circuit should go to 0. So therefore, we already know a way through which we can force the output state of the flip-flops to go to 0. So this needs to be made 0. That is, this 6 is by default 1, 1, 0. So this I will try to make 0, 0, 0. So therefore, we already know how to make this happen. We are already aware of another input which is normally present with every flip-flop, that is called as a clear. Okay, so let us say each of these inputs or each of these flip-flops has an input called clear, which is an active low input. That is, when the clear of each flip-flop gets a 0, then that state variable of the flip-flop forcibly becomes 0. So now, what we essentially need is when the output tries to go to 6. That is, if this we take as the MSB and this one we take as the LSB. Then when the output is trying to go to 6, then Q2, Q1 and Q0 will try to become 110. But only for this particular case, we want that the clear function should be such that it becomes 0 only when this combination is 110. So therefore, I will say clear, I can represent it as a max term. So I can say it is a function of Q2, Q1 and Q0. Now since we are looking for zeros, we can go for max terms. Only 6. So therefore the answer is very simple. 1 is complement, 0 is no complement. That means clear, I can say is equal to Q2 bar plus Q1 bar plus Q0. So I will take Q2 bar from here, Q1 bar from here and Q0 from here. Okay, and I will feed them to a OR gate. I can do that and feed this output to each of the individual clears. That's it. So the moment it becomes clear, all the Q2s or rather all the Q values Q2, Q1 and Q0 will become 0, 0, 0. Alright, and then in that case the clear will no longer get a 0 and then the normal counting sequence can continue. So this is the way you can use clear to forcibly make the output state of each flip-flop a 0. Likewise, you can also use the presets to force the outputs to 1. Is that fine? Okay. So this is the way with which you can use ripple counters to count in increasing order or decreasing order up to a certain value which is not the maximum or the last value. Alright, so this is a very useful approach. Now, when you say the word ripple carry or ripple counter, once again we are taken back to the fact that these circuits are essentially slow circuits. So when the clock comes to the first flip-flop, until the time Q0 is ready, the second flip-flop will not get the clock. Likewise, until Q1 is ready, the third flip-flop will not get the clock. So therefore, ripple counters or asynchronous counters are very slow counters. So therefore, let us write down the drawbacks. So first thing is that they are slow because Q of one flip-flop goes to clock for next flip-flop. That is why they are very slow. Next, we have seen how to make ripple counters using T flip-flops. We also said we can use JK flip-flops because for J and K equal to 1, the criteria of the next state being equal to the complement of the present state happens. But if I tell you, make a ripple counter using either an SR flip-flop or a D flip-flop, that will become impossible. Because for SR flip-flop and D flip-flop, there is no combination which will give you a next state which is equal to the complement of the present state. So therefore ripple counters, you cannot make them easily with SR and D flip-flops. So we'll say specific to the type of flip-flop used. So in bracket we'll say works well for JK and T and difficult for SR and D. So therefore something tells us if a technique is not very useful for all flip-flops, it's not really, worth pursuing that for very long. Next, we've already established there are two drawbacks. One thing is slow speed, the other thing is it is specific to the type of flip-flop that is being used. As if these two drawbacks were not enough, the third drawback is what we discussed today. You need to alter the circuits little bit depending on whether the flip-flop is positive edge triggered or negative edge triggered. So I'll say sensitive, or I'll not say sensitive, I'll say depends on positive edge triggering, negative edge triggering of the flip-flop. Meaning, although it's not very difficult to design a counter, whether the flip-flop is positive edge or negative edge triggered, but then some small minor changes need to be made in the circuit if we suddenly decide to replace the negative edge triggered flip-flops with positive edge triggered or vice versa. So therefore we need a circuit which can be used universally without worrying about whether the circuit is positive edge triggered or negative edge triggered. So these are the drawbacks of ripple counters. And therefore, these ripple counters or asynchronous counters, they don't find that much of use in real life, unless there is some real difficulty with having the clock going to multiple flip-flops. So the opposite of ripple counters or asynchronous counters is what we call as synchronous counters. The opposite of ripple or asynchronous. So the advantages of the synchronous counters would be exactly the opposite of the disadvantages, that is they are faster. Why they are faster? Because each and every flip-flop in the counter gets the exact same clock signal. Each and every flip-flop in the circuit gets the exact same clock signal. So all changes happen at the same time. Next, synchronous counters do not depend on the type of flip-flop being used. So can be designed using any flip-flop. Can be designed using any flip-flop. Third, it does not depend on the positive edge or negative edge triggering of the flip-flop. It does not depend on the positive edge or the negative edge of the flip-flops that are being used. So it's like saying if I have 3 flip-flops, it does not matter what kind of flip-flops they are. They can be SR, they can be T, they can be D, they can be JK. So suppose they are positive edge triggered, then the clock is like this. But this clock is also used to feed the next flip-flop. And same clock is used to feed the next flip-flop. So effectively what happens is that the same positive edge or negative edge of the clock goes ideally equally to all of the flip-flops. Hence, depending on what the input of the flip-flop is, all of them can change at the same time. Now let us say this is T0, Q0 and Q0 bar, T1, Q1 and Q1 bar, T2, Q2 and Q2 bar. Now let us say, for the sake of discussion, that the input to the T's are all ones. Then, as you know, for the T flip-flop, the state table looks like this. So therefore, if you assume that initially all the Q values are 0, then if the clock comes like this, and let's say they are positive edge triggered. Now since we are giving the same clock to each, it hardly matters whether the flip-flops are positive edge triggered or negative edge triggered. So therefore, if you assume that Q0 is initially 0, then in the first positive edge it will become 1. And this 1 will stay until the next positive edge. Here also it will change in the next positive edge and will change in the next negative edge, and so on. Q1, now it comes the difference. Q1 is getting the exact same clock as the first flip-flop, so therefore it does not depend on Q0 anymore. It will depend only on this first clock. So therefore this also will change like this. And so is Q2, because Q2 also depends only on the clock, not on Q1 or Q0. So what we are seeing is that it's as if these three flip-flops are three independent elements and are working identically because they are giving the same output. So but the output does not seem to make much sense. It goes from all ones to all zeros, again to all ones, to all zeros, again all ones, and so on and so forth. It's not really counting. It's just switching from maximum to minimum, then to maximum, again to minimum, and so on. Now comes the question. If every flip-flop gets the same clock, which is independent of the output from any other flip-flop, then how can we design that circuit to be able to count? How can we design that circuit? Well, now this is where things get a little challenging. Now we need to ask ourselves, what would be the best way to proceed in this particular problem? So let us say we want to design a synchronous circuit that counts all the way from 0, 1, 2 till 7 and then again 0 and like this. So let us just draw a diagram for better clarity to see what the counting sequence looks like. Alright. So after 7 what happens? it should come back to 0. This is what is needed. We want to design this up counting sequence using the synchronous counter using T flip-flops. So effectively what we would like is that this count should be coded inside Q2, Q1 and Q0. This is the counter or the counter state. All the values, if it is 0, 0, 0, should reflect over here. If it is 1, 1, 1, it should go over here, like this. Now suppose I know what is my Q2, Q1 and Q0. Let me call this as my present state. Let me call this as my present state. Now if the present state is 0, 0, 0, that is I'm over here. What should the next state be? The next state should be 1. So therefore, I will make one more column. I will call this as Q2 plus, Q1 plus and Q0 plus. Once again, these are not different. I am simply indicating what should be the next state when the first clock comes. So the next state should be 0, 0, 1. Okay. So this is how it is. Now if the present state is 0, 0, 1, what should the next state be? It should be 2. That is 0, 1, 0. If the present state is 0, 1, 0, the next state should be 0, 1, 1. Now this is all the way till we get present state is 7. When the present state is 7, next state must be 0. Okay, so this is what we want. This is what we want. Now, have we achieved anything by writing it this way? Let us look at individual bits. Let's look at Q2 first. I know what is Q2. I know what is Q2 plus. I know what is Q1. I know what is Q1 plus. I know what is Q0 and I know what is Q0 plus. Now, couple of lectures ago, we had mentioned that if we know the present state and we also know what is the next state that we would like to expect, then we can give the input to the flip-flop in such a way that the present and the future condition will be met. And that process led us to the development of a table called as the excitation table. So therefore, corresponding to each and every Q, we can provide some values of T, that is T2, T1 and T0, corresponding to the excitation table. So the excitation table of the T flip-flop looks like this: Q and Q plus and T. We had already derived it. This is what it looks like. So looking at each Q, we have to fill what is the values of T2, T1 and T0. So therefore, let us see how this works. Let us now write the table in detail. Zero, 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 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So then after 0, the next state will be 1, then 2, then 3, then 4, then 5, then 6, then 7, and finally 0. Now to fill the column for T2, we need to look at Q2 and Q2 plus as per the excitation table. So 0, 0 means this will be 0, same state. 0, 0 means again 0, 0, 0 means again 0, 0, 1 means this will be 1, 1, 1 means again 0, again 0, again 0, now 1, 0 means 1. Now time for Q1. We have to look at Q1 and Q1 plus. Be very careful, it can be little confusing. 0, 0, again 0, 0, 1, 1, 1, 1 is 0, 1, 0 is 1, 0, 0 is 0, 0, 1 is 1, 1, 1 is 0, 1, 0 is 1. Next, T0. T0, we have to look at Q0 and Q0 plus. So you can see all are complements of each other. So therefore, this T0 will be all ones. So now you need to solve for each of these cases of T2, T1 and T0 looking at the state variable, the present state only, not the next state, because as I said, these are not different or not different signals. They are the same signal but at different points in time. Okay, so T2 will be some function of Q2, Q1, Q0. So you can quickly make a key map. So the min terms are 3 and 7. So T2 is function of Q2, Q1, Q0, that is equal to 3 and 7. So the K map will look something like this. So we'll call this as Q2, Q1 and Q0. 0, 1, 2, 3, 4, 5, 6 and 7. So 3 and 7 are 1. So I can make a group of these two ones. So therefore T2 will be Q1, Q0. For T1 and T0 we don't really need to make K-maps. We can very quickly find out that T1 is exactly equal to Q0 just by inspection from the table, and T0 is always 1. So therefore the circuit, the synchronous circuit, to realize this particular counter would look something like this. So this is T0, Q0, Q0 bar, T1, Q1, Q1 bar, T2, Q2, Q2 bar. So first thing that we need to do is fill up what is the values of T0, T1 and T2 as we derived. T0 is always equal to 1, pretty much just like a asynchronous counter. T1 we saw is equal to Q0. And T2 is equal to the AND operation of Q1 and Q0. Okay, and clock is over here. The same clock will be fed to the other flip-flops like this one and this one as well. Something that we should not forget is that Q2 is the MSB of the count and Q0 is the LSB of the count. So this is what a synchronous counter looks like. Now if you compare it with the asynchronous counter, if you compare it with the asynchronous counter, we will see that for the same operation, that is to count from 0 to 7, we need this additional AND gate. We need this additional AND gates. Gate power. So the only drawback of synchronous counter is that it gives, while it gives you better speed because the same clock is going to all the flip-flops, but it needs additional logic circuits. In case of the previous ripple counter, this AND gate was not there. So therefore, synchronous counters are little more demanding in terms of hardware. So in this particular lecture, we saw how to work with asynchronous circuits to get the counting up to a particular value that we want, which is not necessarily the last counting value. We saw how to use positive edge triggered and negative edge triggered flip-flops in different ways to get counting sequences. We saw what is up counter and down counter. And thereafter, we established the drawbacks of asynchronous counters, and we moved over to something called as synchronous counters. So synchronous counters, you can design them without having to worry about what type of flip-flop it is, so long as you know its excitation table. So therefore, any counting sequence you want to design, you can design it using any flip-flop that you have, as long as you know its excitation table, and you can design any sequence that you want. So we shall see how to work more with synchronous counters and how to design them to get the desired counting values or counting orders that we would like. We'll also see how we can use them to generate different kinds of sequences or for different kinds of applications. Thank you.